Today we want to talk about gradients in space. We're just adding one more variable to our function. So let's let f of x, y, and z be a function. We want to build the gradient of this function. I could put this on a quiz. I could write tests on this. I could put this on final exam right now and ask you what's the gradient of a function of three variables, and everybody would be fine. If we have a function of three variables, then the gradient of f, the gradient is going to be the I component will be the x derivative. The j component will be the y derivative. And now we're into new territory. What am I going to put for the k component? Holy shit, this is so predictable. All right, so no surprise here. We build the gradient the same way, we just have more variables. Incidentally, if we had a function of four variables, guess what we would do? First, what comes after k? That would be the next component. I don't even know. We'd have an L component. That wouldn't work because L looks too much like a 1 when you type it. Let's not worry about it. So unsurprisingly, we build the gradient in the exact same way when we have a function of three variables. Right now, we might be being suspicious. It's like, oh, what is this function of three variables? At which point it's like, oh, quiet, you. We'll worry about that in a minute. Here are some things that we know about this function, this gradient. If I take the gradient and evaluate it at a point, this will tell us the direction of maximum increase of f. That sounds familiar. No, that's wrong. Be afraid, I just spelled the letter A wrong. A lot of you are like, oh, dude, you cannot spell A with an X. That will ruin my GPA. GPA. So the gradient is going to point in the direction of the maximum increase in f. If I find the magnitude of the gradient, at ABC. The magnitude of the gradient will be the maximum rate of change of the function at the points A, B, C. At this point, we'd be like, oh, this certainly sounds familiar. It only sounds familiar because it is familiar. This part of the interpretation is exactly the same. What word am I going to use next? I'm going to draw a bullet point. What word am I going to use next? Think about the way we interpreted the gradient of a function of two variables. What's the thing that's missing so far? We got direction. Direction is the direction of the maximum increase. Got that. The magnitude is the rate of maximum, the maximum rate of change. Not quite tangent. That's the word that we used before. Normal is close enough. The gradient is going to be perpendicular. Normal. The other thing that we said about the gradient when we had a function of two variables, we said that the gradient is perpendicular to the level curves. But this is a function of three variables. So this is going to be, the gradient will be perpendicular or normal to the level, not curve, if I'm up 1 degree, 1 dimension, what am I gonna call it?
Level plane,
Not plane, plane is always flat.
level,
Level surface. Our interpretation of what the gradient represents is the same. It's just up 1 degree. So things like direction of maximum increase, same. Magnitude is the maximum rate of change, same. Perpendicular to level surface rather than level curve. So here we've got a new thing, level surface. So that level surface part, that's an upgrade from a level curve. We had level curves before, we've got level surfaces now. That's why instead of just saying perpendicular, I got to say normal. Normal is best. I mean, normal is just perpendicular. The gradient was normal to the level curve. But we've been using that in the context of planes a little bit more often. So the gradient is the direction of maximum increase, just like before. The magnitude of the gradient is the maximum rate of change of the function, just like before. And it is perpendicular to the level surface. And this is the part we have to talk about, level surface. That's a good question. Let's think about what a function of 3 variables. How would we classify a function of 3 variables? So, functions of 3 variables. When we had a function of 1 variable, we were looking at a 1-dimensional curve in 2-dimensional space. Y equals f of x was a 1-dimensional curve in 2-dimensional space. When I went up to a function of 2 variables, what did we think of the graph of a function of 2 variables? It's what's the first thing I have to change? Dimension. It's a 2-dimensional surface in 3-dimensional space. This part's going to get a little bit weird, but now we have a function of 3 variables. So if I have a function of 3 variables, I'm going to have something in 4-dimensional space. How many dimensions will my object have in 4-dimensional space? It'll be a 3-dimensional object in 4-dimensional space. What we're doing is taking each point in 3-dimensional space. For those of you not just listening at home, I'm gesturing around the room because we're standing in 3-dimensional space. Right now, it just that some people at home are like, I thought this class was in 4 dimensions. That's why everything was so confusing. But now that I'm picturing it in 3 dimensions, it makes more sense. So I'm gesturing around the room. This is 3-dimensional space. At each point in 3-dimensional space, I'm just assigning another value. I'm putting a height above this point in R4. And then at this point, I just calculate again. There's the height. I know it looks like I'm just moving my hand through 3-dimensional space. I assure you I am not. I am moving it into the 4th dimension. I'm just projecting it down into R3 so you all can see it. Otherwise, it looks like this. See, you can't see it because you're watching me in 3D, not 4D.
40 is often think of at the time.
I don't want time to be I don't want a 4th dimension of time. We don't want to say the fourth dimension is time. What if my fourth dimension is more meters? It's meters, 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 and meters. And what if the fourth dimension is temperature? Meters, 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 temperature. So we have a function of 3 variables. Our thing is going to be 3-dimensional because at each point, we're going to assign a value. So we're going to have a 3-dimensional. Let's call it a solid in R4. The important thing to note here is that our object is 3-dimensional. The other important thing to note is that this object is in 4-dimensional space. It's in R4. And it's meters, 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 and meters. Or this is America. Feet, 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 and feet. I don't know if I've mentioned this, but you know how like we joke about America, anything but the metric system?
I mean, NASA used it.
As if the metric system is better. As if the metric system is better. Prove my point. There was a sinkhole. Have I told you about the sinkhole problem? I haven't told you about the sinkhole problem. There's a picture in the paper, and there was a sinkhole. And next to the and it was a large sinkhole. I will describe the size of the sinkhole. Next to the sinkhole, a minivan was driving. How long was the sinkhole in meters? In feet? I don't care. How big was the sinkhole? It was the size of a minivan. It was actually about 1.1 minivans long and about 1.3 minivans wide. If I say there was a sinkhole the size of a minivan, everybody in the room can picture it right now. You're like, oh, I've seen a Toyota Sienna. There's one in the parking lot. That's a big sinkhole. If I said the sinkhole was 2 meters by 1 meter, are you picturing a big sinkhole?
Honestly.
How big is 2 meters? Is it the size of a minivan? Not even close. How tall am I in meters?
1.5?
A little bit less than 2. And I can lay down in the back of a minivan. But when I said it was it was 1 minivan long, a little bit bigger than a minivan, everybody could picture it. If I had said it was a certain number of feet, you can't picture it. How long is a minivan?
I just know what it means.
See? It doesn't help. It doesn't matter what units we're using when we're describing things. Now, this particular article said that the sinkhole was the size of 7 washing machines. That's fucking funny. But at least you know about how big a washing machine is, right? But if I told you that the sinkhole was 3 meters long, is that the size of a car? How big is your car? Depends on the car, right? I drive a Mini Cooper, a 2-door Mini Cooper. Is it 3 meters long? Less? More? Describing things with those kinds of units doesn't help. If I told you something was 300 feet away, what are you picturing?
Far
Far away, right? But I said it's 300 feet away. Is that helpful? What can you do to make it helpful? What do you picture?
football field.
A football field. That's why we say we measure things in football fields, because you could picture what a football field looks like. It's more likely that you stood next to a football field and seen what 300 feet looks like than if I just dropped 285 feet, or even worse, like 97 meters on you, right? Anyway, what are we talking about?
for the,
four-dimensional space. I had to start thinking about four-dimensional space. So, we can't picture this four-dimensional space. We can't picture this three-dimensional object in four-dimensional space. So we're going to do an exercise. Actually, there's a hint right here. This is how we're going to picture that. Here's what I want you to do. Right. We're actually going to go backwards. What does it look like if I graph x squared equals 4? Graph the solutions of x squared equals 4. What am I going to draw? How many variables do I have here? I just got the one. How many axes do I need? 2. Just the one. I've got one variable, x. All I need to draw is x. And what am I going to graph? -2 and +2. So here's 0, here's -2, and here's +2. That's the graph, x squared equals 4. 2 and -2, that's what it looks like. If we are one-dimensional creatures, we can picture that. It's 2 over that way, 2 over that way. And we're one-dimensional creatures. It's like, oh, dude, I can't see over you, but there is no over, right? That part would be weird. I'm not sure how that would work. What's it look like? I want to graph x squared plus y squared equals 4. What does that look like? I'm going to draw an x-axis and a y-axis, and I'm going to draw what? A circle with a radius of 2. Oops, I missed. I already missed. I got 2 variables, so I'm going to put an x-axis and a y-axis, and we can do this because we are fortunate enough to live in a 3-dimensional environment, which allows us to easily draw 2-dimensional things. Okay, as I easily draw as I struggle to draw a circle.
I mean, circles, pockets, I'll take it.
That's why it's a sketchy circle. To make it blurry.
Try detail.
Called called Bigfoot technique. We get to picture this. We have the ability to picture this because we live in 3-dimensional world. We can imagine 2-dimensional world. We could look right down on 2-dimensional world. No problem. Let's suppose that we are one-dimensional beings and we encounter x squared plus y squared equals 4. Then we have the same discussion that we had about R4. I'm like, oh, well, there's the x, but there's another one. And one of the students in one-dimensional world says, well, that one must be time. I was like, oh, but what if it's not time? Because this is not physics class, this is math class. I don't know what one-dimensional physics look like. That sounds weird to me. I'm going to be thinking about that the rest of the day. There goes my processing power. But anyway, that's beside the point. They can't draw an x-axis and a y-axis. They only have one dimension to work with. So the way they view this circle is they have to view the circle with level curves or level points. So one-dimensional creatures will have to view the circle for a bunch of different values of y. So 1D creatures They can't view this one-dimensional curve in two-dimensional space. They don't have two-dimensional space. They can only picture it in level curves, or sorry, level points. So they have to pick certain values of y and imagine what the picture looks like. So that I picture, what if y is equal to 0? Then they picture these points. And then they picture the level points. What if y is equal to 1? Then they picture those points. So they can just picture pairs of points. They can see that they're evenly spaced about, they can see that they're evenly spaced about their 0 point. But they can't view this whole circle. They can only view it in pieces. It starts off here when y is 0, and then y is 1. And then what happens when y is 2? What do they see? What point do they see when they picture y equals 2? Just that one point. So when they're imagining this, they say, well, it starts off 2 units on either side of the origin, and then it's 1 unit on either side of the origin. Actually, it's 3/2 units on either side of the origin. And then there's only 1 point. So they see those 2 points coming close together. What happens for larger values of y? What do they see? No, larger values of y. If y equals 3, what are we looking at? Nothing. Then they say, oh, the shape stops when we get to y equals 2. After that, nothing. So there's nothing. They see the 2 points starting at plus and minus 2. They see those 2 points getting close together. When y is equal to 2, they see 1 point, and then they see nothing. Because they're one-dimensional creatures, they only have the x-axis to work with. We can also view the other points, like if I drop down to y equals -1. We'll be down here. So they'll see that there's symmetry. They will be able to see the symmetry about the y-axis as those 2 points evenly come in towards the 0. And they will recognize that in the equation. They'll say, that's because that y squared. It takes the positive and the negative and makes it positive. So they see that symmetry working. Then we get down to y equals -2. And we say, we're not going to see anything after this. Those 2 points have come together. And now we're not going to get anything. So there's also nothing after y equals -2. I could say before. So they can't picture this circle because they're one-dimensional. They can only picture these 2 points. They see nothing before -2. As soon as we get to -2, we see 1 point. And then as the y's increase, those points go apart till they're plus and minus 2. Then they come back together when y is equal to 2, and then nothing. That's their view of the circle. That's the only way they have to picture that circle, because they don't have 2 dimensions to draw. They only have 1 dimension to draw things in. Any questions? How's that, okay? What am I gonna write next? I mean, this is like I said, this is super predictable. What am I gonna write next? X squared plus y squared plus z squared equals 4, because I'm not trying to be creative over here. What does this look like? What do we know this looks like? What is this? A sphere of radius 2. Sphere of radius 2, centered at the origin. Minus 1 million for not saying centered at the origin. I'm just kidding. It's minus 2 million. So here we have a sphere of radius 2. Since I'm being a dick about it, center at the origin. We can draw a sketch of this because we can picture in our minds a sphere. I have to draw it, and I have to con you into believing that I'm drawing a 3-dimensional thing. But in your mind, you know it's a 2-dimensional representation of a 3-dimensional thing. I even start by saying, hey, you know, it's a circle, right? And I go, yeah. Circle, right? Yep. But then I'm going to try to give it some depth by giving it a. And I have to fake it. I have to fake another circle. So that's what a circle would look like if it's kind of flattened out. The only reason that we can do that, the only reason we can imagine that, is because we've seen a 3-dimensional sphere before. And I can con you into believing that I've just drawn a sphere. But it's a sphere. But if we happen to be 2-dimensional creatures living in a 2-dimensional world, all of a sudden we're having the same discussion that we had before with R4, and then the same discussion that the 1-dimensional people had with R2. Exactly. The 2-dimensional creatures, they can draw an X and a Y, but then they have to split up the Z because they can't draw a Z axis. They don't have a place to put it. Having these 2-dimensional people draw a Z axis is just like me coming along and say, okay, you've drawn X, Y, and Z. Now draw your W axis. Make sure it's perpendicular to those first 3. And you're like, oh, no. I've used up all the spatial awareness that I have just doing that. And now we're out. We're out of space in our consciousness to draw something perpendicular to these 3. Every time I put another direction on this, it's just in our minds, it's automatically just going to be a linear combination of the 3 that I've already got. But I need to put it outside of that space. So what you do is you put it here. See it? No, I'm conning you again because you can't perceive in the 4th dimension, right? So 2-dimensional creatures would have to view this with level curves. Have you read before? Those 2-dimensional creatures can draw an X and a Y. They can draw an X and a Y, but they can't draw a Z. They have to imagine what it looks like for different values of Z. So we can draw an X and a Y. And they can say that's what it looks like when Z is equal to 0. And then as Z goes up, we get smaller circles until we get to the top. So Z is equal to 1. We'll get a smaller circle. Radius is going to be what, square root of 3. When Z is equal to 2, what are we going to be looking at? Just a point, because we've gone to the top of the circle. Here's where Z is equal to 2. What do we get after Z equals 2, when Z is greater than 2? Nothing. That's when it stops. So they see this circle at Z equals 0. They see that circle shrink down to a point. Actually, by moving my hands up, they don't get to do that. They see that circle shrink down to a point and then disappear. And then we see nothing for Z strictly greater than 2. Then we can also go down the other direction. Z equals -1. We notice they can still perceive that symmetry at Z equals -1. We see the same circle at Z equals 1. Then we look at the equation and say, yeah, there's that Z, that square, turning negatives positive. So that's also Z equals -1. This point in the middle is also Z equals -2. And then we see nothing for Z less than -2. So as we move, we just have to picture the Z at different values. They could even animate this. And then they'll have a little Z at the bottom. It'll be like all -3, and there's nothing there. As soon as Z, and it like counts up, and then when Z hits -2, then they see a circle, or sorry, a point, and then a circle goes out to a radius of 2, and then shrinks back down to a point, then disappears. So they are perceiving they have to perceive this sphere with different values of Z. Now, before we go thinking that that would be them perceiving this through time, they actually don't use time that way. They have those different Z values with different temperatures. So they're perceiving it through temperature. So they can't do Z equals -2 meters. They have to do C equals -2 Celsius. You know what I mean? That's not how we do things in physics. We make time and then we watch things change through time. So, but that's the limit. They can only view these level curves. They can't view the whole object. We get to view the whole object. We're so good at it. Eyes are such a cool thing. We are so good at it that we can say that is a sphere. I don't know what other creatures can look at this and say, oh yeah, and agree that, oh yeah, that's like a ball. I don't know if my dog would look at this drawing and say, oh, that is a drawing of my tennis ball, except it's missing the bite marks in it. So leave that on. I don't think they would do that. But humans, I'm like, oh, that's a sphere. And all the other humans like, oh, sure. And only the most pedantic of humans like, oh, actually,
It's a two-dimensional representation of a sphere. Seems like a trick that you're trying to play on my brain.
And at which point you're just like, oh, shut up. You know what I meant. You know what I mean? What am I gonna do now?
It's time for the,
It's time for the 4D. What am I gonna call it?
I just write it as W.
X squared plus Y squared plus Z squared. This is kind of at the end. Since I'm already invested in this X, Y, and Z, I'm just gonna call the next one W. At this point, I should probably switch to X1, X2, X3, and X4, but we're all X, Y, and Z, so we'll just go W. What shape is this gonna have?
And a 4D version of a sphere because we can't comprehend.
It's a four-dimensional version of a sphere. I don't know, we'll call it what, a hypersphere? Whatever. It's like a 4D sphere. It still has the same properties of all the equations that we had before. Everything that's 2 units away from the origin. It's everything that's 2 units away from the origin. Right now, all of us are kind of what are we gonna do? We can't picture it because I can't draw an X, a Y, a Z, and a W axis. That's not just a combination of X, Y, and Z, right? So what are we gonna do?
We got to see the change in it. Why did we?
We're gonna essentially just pick different values of W. It doesn't matter which one. That's why the symmetry is gonna help us out. But we're gonna pick different values of W and look at the 3D level surface. So us poor three-dimensional creatures are gonna have to perceive this thing through level surfaces. And it's the same procedure. Nothing else changes, except I'm not going to attempt to draw it. When Z is less, oh, sorry, when W is less than -2. So when W is less than -2 or W is greater than 2, what do we see? Nothing.
I mean, it's just a sphere that keeps getting smaller as W.
Right. When W hits plus and -2, what do we see? Just a point, right? Because if any one of these is, if I take up 2, if W is 2, then X squared plus Y squared plus Z squared has to equal 4. If I've got 4 here, this is all positive because real numbers, so that all has to be 0. So X, Y, and Z have to be 0. So when W is plus or -2, we see just a point. We see just the point 0, 0, 0. And then as W goes from -2 up to 2, we see a sphere increase to a radius of 2 and then decrease down to a radius of 0. As W goes from -2 to 2, we see a sphere. It starts off with a radius of 0. That's just the point. And then it increases to a sphere increases to a radius of 2 and then shrinks down to a point and then disappears. We can only perceive this X squared plus Y squared plus Z squared plus W squared equals 4, that equation, through level surfaces. We get to do level surfaces because we can think in 3 dimensions. I can't draw in 3 dimensions. QED, I cannot draw in 3 dimensions. But we can imagine in 3 dimensions. Yeah, I suppose I could have programmed the computer to do something very fancy.
You know, all people are doing, it's just.
Yeah, it's just so we don't really get to use that third dimension on the capability. It's not really useful. Any questions? It's lucky we're 3D. When we, in the 4D classroom, they still start off with x squared equals 4, and then they build up from there. I did a quick internship in an 8D world, and the professor was like, okay, x squared plus y squared plus z squared plus w squared plus v squared plus u squared equals 4. What's that look like? And everybody's like, well, can you just stop? But he had to go through all of them. That's what it's like in 8D world. It's really kind of messed up. It's very boring. You'd think it'd be super exciting, but it's just not.
Exciting is only the measure of how unmanned it is.
Yeah. I thought it was going to be super interesting. And they just kept telling me I just didn't get it because I'm some lowly 3D thing. So I think they were talking behind my back, but since they had so many extra dimensions to work with, I had no idea where they were. It's messed up. Anyway, just a quick reminder, there's no class tomorrow. There's no class on Monday. That's going to do it for today. That's going to do it for this week. I'll see you all on Tuesday. Everybody have a good weekend, and thanks for playing.
I think have a long